All right. All right, so I'm gonna spend a little bit of time to talk about the exam, just so that you guys kind of know, what the correct answers are and how you did, at least, approximately. I think the last question is, kind of one of the interesting questions, so we'll get to that one too. All right, so the first five questions are about the same, but this time I decided to kind of scramble, all the quantified statements too. So the ordering of these, it would not be the same across the questions, but they still look about the same. It's still the same five, they just kind of scrambled. All right, so we'll start with this one. Okay, so let me increase the magnification. There we go. All right, so there are a few things, when you read this, the first thing is, to understand the quantified expression itself, and then it also helps to kind of see if it maps to something that you already know about functions, okay? There are five things, to know about a function. Three of those relate to whether it is a function or not, and then the other two, tells you whether it is injection or surjection, if it is a function at all. But each one individually can also still be evaluated and give you an answer of either true or false. So even if f is not a function, you can still answer the question of whether it is true or false. And then also, if the statement is universally quantified and false, then you have to specify how the boxed portion can be made false. If the statement itself is existentially quantified and true, then you specify how to make the boxed portion true. So, that's the second part of answering the first part, which is what is the value of the expression itself. All right, so we'll start with this one. Okay, so the way we read this one is there exists GH as an element in F. There exists an element UV as a two-tuple in F, such that G does not equal to U and U equals to V. Okay, so now the question is, which part of the five things about functions, does it relate to? So that's really the question. So because we are looking at tuples, GH is a single tuple, UV is also a single tuple. So now you basically have to look at, okay, so which part of the two tuple is not the same and which part is the same? G and U are both referring to the first part of the two tuples. So we are basically looking at the element from the domain, okay? And then the other two are the second part of a two tuple, so they are elements or element in this case because it equals to on the codomain side. So this is basically saying, okay, with two different things from the domain, they map to the same thing in the codomain. So what does it relate to? Hmm? No, no, no. But in the general discussion of functions, what does it relate to? Okay, Daniel, you had your hand up. Yep, that is that is correct. So if this is true, if the existentially quantified expression is true, is F an injection or not an injection? We're looking at evidence that it is not an injection. That is correct. Now, does F have to be a function? No, because these expressions do not tie into X or Y. It really is just saying, okay, look at the pairing here, and we're just looking at the pairing or the two tuples. All right, so that's good. So we can now, I'll just kind of write it on the. Obviously, I cannot because I don't have any dry board markers. Okay, so that's okay. I can use mouse pad. Mm, all right, so we can do it like this. Okay, so we can say, for this particular question, part zero is So this is not part of what you need to do, okay? But just for explanation purposes, I'm going to explain this. Okay, so the statement is true only if F is injective, okay? Or the statement is false. Okay, there we go. I forgot to mention that. False only if F is injective. So in this particular question, we are asking, do we see two different two tuples mapping two different elements from the dome from mapping two different things to the same thing. Okay, that would be the best way to do it because we cannot use the term domain versus codomain because we may this may not even be a subset of the Cartesian product. But we don't see it, right? C maps to C, K maps to H, and D maps to D. We do not see something like, oh, okay, on top of C maps to C, we also see C maps to A. Okay, so that is lacking. So that means in this case, the statement is false. Statement is false, which also means there's nothing else to do because this is a existentially quantified statement. And according to the second part here, if the statement is existentially quantified and true, but this one is false, so there's no additional things that we need to do. Oh, right. I can- oh, okay. Each one, okay, you're referring to the second portion here? That is correct. Nope, nope. Yeah, these two are in addition to the first part. So these are basically conditional parts where if the condition is not true, I know we are doing some really kind of meta things about conditions and conditional statements and implications. Huh? Oh, okay. Because I was just trying to make it, actually more clear compared to the practice exam. Oh, is it? Was it? Darn it. Okay. Yeah, basically it's saying, if the statement is universally quantified, that implies you have to specify how to make the boxed portion false. And then the statement being is substantially quantified and true, then you also have to specify that. Oh, okay, I see. I see what you mean. Okay, go ahead. Too many words. Do you? Okay. I really hate to be this blunt, but sometimes I feel the necessity to do so. Do you plan to work? Do you plan to work? Do you plan to get a job? The the job description itself is going to be far more complex than what we are dealing with here. I just want to point that out, okay? Because yes, go ahead. What was the other? Yep, yeah. It, it, what I'm looking for is the same style as the practice exam. This is just a different prompt to ask for basically the same thing. So when we get to the question where the secondary part is comes into play, I'll show you. All right, so this is the first one, and then we look at the second one. There we go. So the second one says for all E in Y, there exists UV in F such that E equals to V. All right, so once again, it is important to, now this time we are looking at Y, okay, which is the potential codomain. So we are basically asking if F is a function, then we are asking, can we show that for every element in the codomain, blah, 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 blah. Okay, so right here, I can almost come to a close to conclusion that this is probably asking about surjectiveness. or related to surjectiveness, but not always. Okay, so we'll read a little bit further. So for every element in the codomain, if f is a function, there exists a pairing in f such that some u, okay, is mapping to this e in the codomain. Okay, so now I'm confirming that this has to do with surjectiveness. Then the next question is it what is the polarity of the answer? Okay, is it surjective if this whole thing is true, or is surjectiveness false when this whole thing is true? What do you think? That is correct. Yep. If every element in Y is mapped to in F, then the function is surjective. Yep. Hmm? Yeah. So we don't know yet whether it's a function or not. Yep. Hmm. So we'll say so if true, surjective. Okay, that's how we're going to put it right now. So in this particular case, is it true? So now you have to look at all, so you have to procedurally do it the same way as what the quantified expression is telling you to do. So now we go through every element in Y. We look at C first. We ask, is C mapped to? Yes. We look at H, is H mapped to? Yes. We look at D, is D mapped to? And also yes. So in this case, the statement is true. Yep. Yeah. So if you look at only the outermost portion, it is universally quantified. Yep. Okay, that's a very good point. I should have said excluding the boxed portion. Yep. No, this is universally quantified because yes. So you are correct. This entire condition is false. Yes. Yep. Because you have because you have the statement is universally quantified is actually true, but the value of the entire expression is false. So that's why no, the value of the entire expression is true. So that means you do not satisfy this portion. So that's why the conjunction is also false. Yep. So I should have said if the statement excluding the boxed portion is universally quantified and then the entire statement evaluates to false, then specify how to make the boxed portion false. Mm, okay. Uh, you guys can come ask me what kind of format I'm expecting from the answer, right? I mean, hmm? Yeah, that is true. That is one hiccup, with taking the test at the DSPS center. All right. Shall we move on, or you guys kind of get the idea already? Finish the whole thing? Okay. All right. Cool. Okay. So part two. Okay. So zero, one, and two. So this one is also universally quantified. But okay, look at these two. This, this is interesting because they are side by side in this case. So you look at this and you look at this and go like, oh, Tack, did you make a mistake? Aren't they the same? The answer is no, they are not the same. This one has the universal quantifier on E being an element of Y. This one is on X. Okay. So this one is basically asking, Is it true or is it false that for every element in the supposedly domain that it maps to something in the codomain using F? So does it map to something? Okay, so the answer is what does it relate to? Okay, the statement if true, it meets what requirement? It meets one single requirement, which is it is a part of whether F is a function. Hmm? Well, let me write this down first. Okay, if true, um, it F satisfies one of the three requirements of being a function. All right, so in this case, in this for this specific one, is it true or is it false? So X has D, K, and C. So we ask, does D map to something? It can be mapped to it can map to two things. Okay, it will still make it true. D maps to D. Okay, cool. What about K? K maps to H. Cool. C maps to C. Cool. I don't even bother to check whether the other C is actually in Y or not because that's not what the question is asking. So in this case, the statement is also true. All right. We don't even know whether it's a function yet because remember, this is one of the three requirements for f to be a function. So we don't even know whether f is a function. I mean, you can eyeball and say that it is, but it is surjective and injective. Yes. hmm Okay, so from this one statement itself, we know only one thing. We know that every element in X maps to at least one element in Y. That's all we know. Now, can each element of X can one of these things map to two different things, which makes it F, which also makes F not a function? We don't know yet, okay? Because we are not concerned about how many things we are mapping to. We're just concerned about is it mapping something. And we also do not even know whether the second item of the two tuple, we don't even care whether it is in the codomain or not by this requirement by itself. So it is a very restrictive requirement that needs to be true, but by itself is insufficient for f to be a function. This is a necessary condition, one of the three necessary conditions in the context of these questions. It is not meant to be. Yep. All right. And what about three? Okay, so we'll scroll up a little bit. Oh, wrong mouse. Okay, so three right here. What is the value of blah, 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 blah? And then this time we are looking. Okay, so this time it's double universal quantifier. So for every GH in F, for every UV in F, can we check to make sure that G equals U implies H equals V? Okay, so now the question is, what is it really checking? So we are basically saying, okay, we take possibly two, okay, two tuples from F, and then we say, if the left-hand side is true, does it always guarantee the right-hand side? Because if there are two tuples, both mapping from the same element of the same element on the left-hand side of the two tuple to different things on the right-hand side of the two tuple, then we have a problem because it will make it not a function. Okay, so that's the context or that's the semantic of this particular one. So we say if true, f is not a function because one thing maps to at least. Oh, Say that one more time. You don't have to write anything, I mean, because in this case, we have to ask you, is it true or not? Okay. No, because I want to explain how it relates to the concept of a function, which is not what I'm asking in the test. But the point of these questions is to see whether you can relate it. Okay, so right now we just check this. Okay, so we ask, okay, let's take a look at what was it? It's number three. So we ask, so this time it's a little bit more complex because you have to do the pairing. Basically, you have to look at CC versus CC. So CC versus CC means that this implication is true. We all get. CC versus KH means this implication is also true. We all get. Wait, how can they be true? CC versus KH? Because C equals to K is false. If the left-hand side of an implication is false, the implication is automatically true. So now we look at CC versus DD, also automatically true because C and D are different. So the only thing really left is KH versus DD, which is also going to be true because K and D are different, so we don't really care what they map to. Are we good? Okay. So in this case, so I'm gonna say if false. Sorry, that's my mistake. If false, f is not a function. But since it is true, so that's nothing we need to do here. Okay, the statement is true. Okay, so here comes the last one, and you probably can guess which what the last one is about because we have already talked about injection, we talked about surjection, we talked about the two out of the three requirements to be a function. So this is the last one. So the last one is really just checking, okay, um, there exists an element E in F. So this time the two tuple is seen only as a one single thing, which is E, such that it is not the case that E is in the Cartesian product between X and Y. So this is the double check to make sure that every two tuple in F has something from X as the first item and has something in Y as the second item. So that's the last requirement for this thing to be a function. So we'll say um, if true, f is not a function because f is not a subset of x times y. Okay, so in this case, what is the answer? So how do we evaluate? Okay, so in this case, how do we even evaluate? So we look at every element in F, CC. Is that in the Cartesian product between X and Y? Yes. KH, yep, K is here, H is here. DD, yep, D is here, and then D is here. So that means for every element in F, the first item is always coming from X, the second item is always coming from Y. So for this particular case, the statement is also true. Oops. Nope. There we go. Are we good so far? Yep. Oh, right, right. Yep. If false. There we go. Yep, there you go. All right. So now we move on to number five. Okay, here comes number five, which is phrased exactly the same as the other one, as the practice exam. Okay, what is blah? Okay, points are allocated to subparts, even that is identical. So in this case, f is a function, mapping x to y is actually true. So now we have to go for that part. Okay, so we have to say 5.1. We say it is true. Okay, quote which previous parts or parts of the answer lead to this conclusion. The subtext on top here actually asks which part is true and which part is false, but since I did not really specify that in the practice exam, so I'm gonna go like, okay, I'm not gonna look for that. Okay, for people who did answer that, it's okay, but I would not be looking for it. Yes. Oh, number four. Wait. Okay, hold on. Okay, so for number four, the answer is false. Oh, okay, yeah. If it is true, then f is not a function. You're correct. Yep. The statement is that is you're correct. The statement is false. Yep. Thank you. All right, 5.1. Okay, which three relate to whether f is even a function or not? So in this particular case, I have to go back and look. That's about injection. That's about surjection. So it's 2, 3, and 4. So 2, 3, and 4. It just so happens. And then we have 5.1.1. But this part is the same as before, okay? If S is F injective. So in this case, it is injective because number 0 is false. Okay? It is injective because of 0 is false. But I'm not looking for that. You just have to mention 0 because of 0. But you do have to confirm that it is injective. So 5.1.2 surjective because of 1. That's it. Okay, so you're asking about, you mean this part here? So it's the correct answer would be 2, 3, and 4. Yep. Mm-hmm. You get partial. Yep. Yep. To answer 5.2, yep, you only need one. And some of the functions can have multiple reasons why it is not a function, but if you state one, it'll be fine. That'll be sufficient. Because to show that something is not a function, you just have to say, oh, it's missing this requirement because the three requirements are necessary requirements. So if you miss one necessary requirement, then that's enough already. But because they're all necessary requirements for f to be a function, so when I ask why f is a function, you have to quote all three. Hmm? If it is false, only one is required, even though there might be multiple ones. Yep. Alrighty. Yes, that is correct. Number two does not specify why, so the best way to specify two, or you can say every element in X maps to at least one thing. Because we have to drop the requirement that it is from Y because that's not what the statement says. Yes. Well, yes, because number two is missing two things because it's not checking whether the element is mapping to something in Y. It doesn't specify Y. It also doesn't specify it has to map to one and only one thing in Y. So it's missing two things. Yep. If you're missing two and only have three and four, those are not enough to conclude f is a function. Because if you look at three, okay, so what does three says? What does three say? If false, f is not a function because one thing maps to at least two different things. So if it is false, that means there will be no f. We know that um, everything maps to up to one thing. Yes. Yep. Yep. So two and three work together to say one and only one. Yep, to say one and only one. So two and three they work together to specify one and only one, and then four is locking down everything to be inside the subset of the Cartesian product. So everything that is all the first item of a two tuple, they have to come from X. All the second item of a two tuple, they have to come from Y, because those are missing from when you look at just two and three, that particular message is missing. Yep. So that's why two, three, four, they're all needed in order to express the whole thing. Yep. All right. Are we okay so far? Yep. So in my attempt to make the language more precise, I kind of achieved the opposite. So yeah, being paradoxical is my life. Don't ask me why I said that. Paradoxical. Now, paradoxical is not the same thing as contradictory. Why? No. Yes. Yep. And but finish your sentence. Go ahead. Yep. Paradox is no, but you're spot on. A paradox means you have two things that appear to be opposite to each other, but they're actually consistent if you look a little bit deeper. Contradictory or contradiction means those two things cannot be true at the same time. Period. Hmm? This is more of a philosophy kind of thing. My 310 class? Yeah, what about it? But that's exactly what they are. Because at okay, but I would like to address that statement because it really is important for us to be able to see computers in that way. Because at the underneath everything, okay, what is actually storing the state of your registers and whatnot? They're all transistors, okay? Everything is a transistor, okay? So what exactly is a one and what exactly is a zero? It is the interpretation of the voltage of the output, okay, of a gate, which is basically the output of the combined output of some register of some transistors. So if you look at the hardware level, there's no intrinsic meaning whatsoever. Okay, there's just voltages, and they're not even zeros and ones. Okay, they're all over the place. We're just asking, is the voltage here above a threshold? If it is, it's a one. We interpret it as a one. Or is the voltage here less than a certain threshold? If so, we interpret it as a zero. So it's all about interpretation. So when you have a byte or 32-bit thing kind of string together, when ordering is important, you can look at it as, oh, okay, I think that means 32 pixels on the screen, which pixel is lit, which pixel is not lit. That's one way to look at those 32 bits, right? But you can also look at it as four individual characters because one character is a bit. You can also look at it as a 32-bit integer. You can also look at and then you have to say whether it's signed or unsigned. Or you can look at it as a float, which is a single precision floating point number. Hmm. So they are talking about endianness. not Indianness, but Endianness, Endian. So that means what byte gets transmitted first. Mm. That's what I'm guessing because Endianness does not pop up unless you're talking about a transmission. Because transmission is byte by byte. So that means if you transmit the most significant byte first versus you transmit the least significant byte first, then we have a communication issue, right? Yep. And that's one of the main differences between architectures. Some architectures are big endian, which means the most significant byte has a you know is at a lower address when you look at ordering. The Intel architecture is little endian, which means the least significant byte is at the lowest address. Hmm? Right, right. Yes, that's because the smallest unit of transmission is a byte. So you cannot mess up the ordering of what is inside a byte or between the bytes. Okay. Yep. So those are interesting concepts. I think computer science people really should understand those as well, even though most people associate those concepts only to networking. All right. So let's go to number six. Okay. So number six has three parts. Okay. So we'll address 6.1 first. Using the Cantor's pairing function g introduced in the Aleph null module, g of xy is known to be exactly 1295 for some xy in the set of natural numbers. Step by step, show how you find the values of x and y. The final answer of this part should be in the form of x equals to something, y equals to something. All right, so how do we do this? I cannot remember how to do it either. Okay, just like you, I go like, what is the inverse function again? So what you do is you go to the Aleph null module, and this is also why I asked you guys, to put all the definitions and all the functions in at the same place, because now you only have one piece of paper to carry with you. All right, so we go to here. And then we go all the way to the inverse function. Because we are given n already, we need to reverse n, which is a single natural number, back to the x and the y. So you can plug it into here, figure out what is wn, and then plug it into here, or you can just show me step by step how you did it. So I'll just go ahead and do this part first. Okay, so we have, I need to look at the question first. All right, so we have 1295. Okay, so n equals to 1295. Okay, and then we go back to the notes, and then we ask the question, what is the floor of the I'm typing this carefully because I want to kind of use a spreadsheet to do all the actual calculation. So we're looking at the square root. Okay, we need to blah blah minus one, and then the whole thing divided by 2, and then take the floor of that. Okay, so inside the parentheses here would be whatever is inside the square root. So we have the square root of 8 times n plus 1. There we go. So now we just plug this in. Okay. You can probably do this without a calculator, but it's going to be a little bit painful. So copy, and then just open up. I'll just use a spreadsheet for this. So we go to my drive. So the key is you have to show me the steps too, okay, not just a single answer. So then we go to shared, open a new Google Sheet. 2025. Oh, nope, today's 10:01. All right. So equals, and then the whole formula. Okay, what did I mess up? Square root. No, square root is correct. Floor is correct. All right, so why does it complain? What is it complaining about? Oh, and right, right. It's 1295, I think. There we go. So WN is 50. All right, cool. So now that's the first step. So we say W is X plus Y is 50. So whether you use the function reference or whether you just look at W as W itself, I don't care. Okay, so that's fine. Okay, so we just now qualify this. This is our W. All right, so from here, where do we get Y? So now we have to ask, okay, what is the G value of W0? So that would be 50 plus 51, oh no, 50 times 51, the whole thing divided by 2. Okay, 50 times 51 divided by 2, and that is, I'm just going to cheat over here too. So we just look at this number times this number plus 1, the whole thing divided by 2. It is 1275. So now we also know that g of xy is going to be g of w0 plus y. Okay, so I'm just going to pause here. Okay, does everybody understand why g of xy is g of w0 plus y? Because w is x plus y. Okay, so now this is 1275 plus y. But we also know what the other side is because that's the end that is given to you, which is 1295. So now we have everything that we need to solve for this y. Y is, in this case, 20, I think. Is that okay? So something like this, okay? You can use the other way, which is plugging in WN, all over the place and do all the multiplication, okay? I think this is a little bit easier and quicker, but it's not the only way. All right, so that's 6.1, and then we move on to 6.2. 6.2 is asking, figure out the number of UV, or the number of elements in the Cartesian product of natural number versus natural number that are on the same diagonal line as the coordinate that you solved in the previous part. So you just say x plus y is the number of, oh, actually there's a plus 1. Plus 1 is the number of elements on the line, on the diagonal line. Diagonal line. In this case, it will be 21. Do you know why there's a plus 1? What is the quickest way to realize that it's not just x plus 1, it's not just x plus y, but it is x plus y plus 1? What what edge case do you use to realize there's a plus 1? Where does 0 go? Which pixel or which coordinate has 0? It'll be 0, 0, right? So how many cells do we have on that particular diagonal line? 1. So that's how we can tell that there's a plus 1 in the whole thing. If you miss the plus 1, you're not going to miss a lot of points, okay? Because you get the gist of it. Okay, so what about 6.2, 6.3? Derive the first element, which is basically just asking what is x0 in this case, and the last element, which is just trying to figure out what is y1 on this diagonal line. Okay, so we'll just say that 0 is exactly w. X0 is w, which in this case is 50. And then y1 is Also 50. So it is also W, which is 50, because um, because 50, 0 is the first or bottom coordinate such that such that um, x plus y equals to 50, and same explanation for the other one. So you don't have to use exactly the same words. I just need to see, you know, how you come up with the values, and just a really brief explanation of that. You can even give me a picture, like a just a really rough picture, and say, oh, this is the one that has, the y coordinate being 0, and it is, just W itself, and over here we have the other one. So there are many ways to convey the same message. All right. Are we doing okay so far? I can see Ari's face is like, no. Well, it is, but it goes beyond that, because it means that you can actually map any dimension of natural numbers down to a single dimension. You can fold dimensions. Okay, let me elaborate. Mm-hmm. Yep. Okay, so since you made a presentation, I know the rest of the class, most people miss, Ari's, excellent presentation on 3D projection. So let's say we have X, Y, Z, as a three-dimensional, point, right? So now we can say, okay, how do we map this to a single natural number? So now we just go like, oh, okay, we can just apply G to it. And you go like, but wait, Tech, this won't work because G only applies to two natural numbers. We have three now. Fine. Happier now? Yes. So you can repeat this process recursively. I know how much you guys like that word. So you can do this recursively and reduce a multi-dimension coordinate to a single natural number. And the nice thing is you don't need to store the dimensionality, because as you apply the inverse function, you will know when to stop. Hmm? Yep, yep. Otherwise, you just get a bunch of zeros. So by the time you get to 0, okay, we're done. Yep. Okay, so imagine you're in a multi-dimension space, which we are. Okay, this is a three-dimensional space, right? It means there's a way to map every single point. If it is quantized to natural numbers, we can map every single three-dimensional point to a single natural number. And we are assuming this space is infinitely large. That's what we can do. But you can also increase the fourth dimension, the fifth dimension. It doesn't matter. We have a way to reduce the number of dimensions, and when applied recursively, it can reduce any fixed number of dimension to a single linear dimension. Yep. But it also has another really kind of interesting application. I can encode an entire string of an unknown length to a single natural number using the Cantor's mapping function. Now, does it really buy you anything? The answer is no. You actually ended up using more bits than you really need to represent the string, but you can do it. Oh, it would be super annoying because you're looking at a gigantic bit pattern and not really know how the characters are encoded. hmm But you can do it. Okay, so from that perspective, the Cantor's mapping function is fascinating in the sense that it illustrates the concept of L of no. So if you want to take colors into consideration, which is just RGB, right? RGBs are natural numbers. So you fold the RGB into a single number, and then you fold the coordinate into a single natural number. Now you have two natural numbers, one for the color and one for the coordinate, and then you fold that also into another natural number. So you can use a single natural number to convey where that pixel is and what color does it have. And it's but the original idea of presenting Cantor's mapping function is only to emphasize that you can fold two-dimensional space into one dimension. Now, folding integer into natural number is already kind of fascinating. Um, and therefore we have Aleph no is the first one, and then we have Aleph one, Aleph two, and so on. Yep. So it is about the equivalence of infinity. And in this case, it's called countably infinite. So even though you have an infinite number of things, we can count all of those using just natural numbers. All right. So are we ready to move on to we or back to propositional calculus or propositional logic? You guys vaguely remember that? Okay. All right. Okay. So what we'll do today, okay, we still got about half an hour. I think I can get some material out or across. All right, so let me first, get back to my tablet, and we'll see whether we still cannot make a connection today using the five gigahertz frequency, because I think something else is around here using the same frequency, and that's why the interference is causing this thing not to be able to pick it up. I think my laptop computer probably has a better antenna, more sensitive or more tuned to exactly the frequency that it needs. This one is not. So we'll see. Okay, turn it on. There we go. All right. So does anyone remember the relevancy of propositional logic? Why do we care? Yeah. Not quite. Okay, so propositional logic is a formal system so that you can determine whether a bunch of statements that are known to be true will imply a particular statement that you want to be true. Or known to be true, you just need to find the connections. Yep. All right. So let me hook up this side to the same Wi-Fi. Yep, it cannot see that one either, but that's okay. Yeah, I think something around this room, because of proximity, is using the 5 gigahertz frequency and is not playing nice with other routers of the same. It's this room because 306 does not have this problem. 305 doesn't have this problem. My office doesn't have this problem. It's only this room that has this problem. But hmm, Yeah, sure. If I know the frequency of your neural link, that is not a good thing to have. Not a good thing to know. It's not a good thing for you to know that I know. I don't think so. Okay, so X-ray is not an issue because X-ray is just photons passing through your body. A CAT scan, on the other hand, is a whole different thing. It might just pull the implant out of your head in a direction that you may not prefer. It can cook it too. Yep. No, it's alternating. It's not, well, it is spinning, but it's spinning pretty slowly like this. But the magnetic field that is emitted is at a high frequency. It's that is going to induce a current on anything that is conductive. Yes. And that's why they want people to remove all the rings and necklaces or body piercing of any kind that is metallic because otherwise those will all get heated up or get pulled out of your body. I should say tear. What? Yeah, I use that to teach Cisp 310. Yeah. Yeah, the switches, the railroad and the switches. Yep, yep. Because we actually look inside the processor as well, the way I teach it. Um, hmm? The train, no, that would not be. Well, I mean, in a certain way, it's you can kind of force a connection there, but Bob the Builder. Hey, I use SpongeBob to teach base conversion too. The reason why I use SpongeBob in that case is because of converting bases to 8 and sometimes 7. Seven because it has to do with drunk octopi because drunk octopi needs one hand to hold a beer or one tentacle to hold a beer. All right, so I think we're good here. Let me go back to the notes for this class. Notes 440. There we go. All right, turn on screen share. All right. I think for the first time we are getting this to work. Woohoo! Yes. Hmm. All right. So this time, when we talk about propositional logic, we are going to kind of introduce the concept, step by step. So propositional logic has five. It's a five tuple thing, okay, which means there are five things that are important when you want to specify a propositional logic system or propositional calculus. There's one set called alpha. This is alpha. So typically what we put in alpha are symbols only, okay? 0 and 1 are constants. Okay, in this class we use 0 to represent false, 1 to represent true. So they're constants, which means they cannot assume any value other than, in this case, false versus true. And then I typically use P, Q, R, S, T, okay? uh, lowercase letters from the English alphabet to mean variables. Okay, so each one can be true, can be false. Just by looking at it, you don't know whether it's true or false. Is that okay? And then I typically use some Greek letters too. I like to use rho, alpha, no, sorry, theta, and rho and psi. Okay, so psi is one of the ones that I like to use. I mean, you can pick whatever you want. Okay, the idea is we have constants, we have variables, and then we have what we call schematas. Okay, so right now it's pretty hard to specify or to tell you what a schemata is. Okay, but you can look at it as a wild card. Okay, it can be used as a placeholder when we say, I don't care what is here. We'll just call that psi. Or I don't care what is here. We'll just call it rho. Okay. The other way to look at the Greek letters is they can be expressions. Okay, they're placeholders for entire expressions, as in Boolean expressions. Okay, so that's alpha. Alpha gives us exactly alphabets. Okay, the most elemental things that can exist in a equation. All right, but I guess it will also be helpful to kind of tell you what PKRST can be representing in real life. So PKRST can represent things that can either be true or false or statements. So what kind of statements are we talking about? That sounds awfully abstract. So P can be the statement that says, Tech is an awful professor. Okay, can be true, can be false. Okay, now in reality, assigning that statement to a single variable is probably not a good thing to do because it probably is a function of who is evaluating, right? So, but we'll just say that, well, for the sake of this argument, it is a variable. It's either true or false, but looking at the statement itself, we don't know whether it's true or false. And that's why, using a single variable, is not the best way to do it. It doesn't give you the flexibility. True. I like that. It's so meta. But anyway, P is just, the variables are really just statements. Okay. Each one can be true, can be false. Are we good? All right. So the next one is omega. Okay. So omega is called the set of connectives. Okay. That's the name. Okay. I didn't pick that name. So it's the set of connectives, but from your perspective, they're just Boolean operators, okay, or Boolean operators. So we typically have negation, okay. We can have and, we can have or. In this class, we also talk about implication. We also talk about equivalent to, and so on, okay. But we'll just typically put these five into omega. So there are a few more, okay? There are two more things, that makes up a propositional logic system. But I will pause here, okay? I'm going to take a pause, not because I'm going to let you guys go 15 minutes earlier, but instead, I want to talk about what is a well-formed formula, okay? So a well-formed formula. It is correct, okay? It is WFF, not WTF. I know you guys go like true, false, right? The middle character is either true or false, and that's why it is WFF. No, it is because it is well-formed formula. So well-formed formula is basically saying, okay, structurally speaking, how can we use the operators to make syntactically correct expressions? That's it, okay? So now we go like, okay, everything is out in alpha is by default LWFFs. Okay, they're well formed. So if you look at 0, it is well formed. If you look at T, it is well formed, and so on. Parser? Parser? No. No, no, no. This is all basically setting up the structure of what is a well-formed formula, because otherwise I won't have the vocabulary to express the rest of this. Okay. But you can also apply a unary operator when there's only one argument. Okay, so that means the negation of P is also well formed because this operator, which is here, is a unary operator, which means it takes only one single operand. So if I give it just one operand, we get. Okay, but if you use it as if it's a binary operator, set in the sense that it takes two operands, not good. That's not how it's supposed to be used. Is that okay? But you can also take one of the binary operators, which means it takes two things, and go like, okay, what if I just say and R? Okay, nope, that's not good. Okay, because and requires two things to operate on. You cannot just give it one thing to expect it to give you the answer. But on the other hand, if you have S and T, then we're good again. Is that okay? So now we go recursive. Okay, I like how I think I know how much you guys like that word recursive. So now we can say, oh, so can we take two things that are already well formed and make something bigger that is also well formed? Exactly. That's exactly the point. Okay. Take this one and we'll take this one over here and we'll say, so if not P is well formed, what about the disjunction between not P and the other one, which is S and T? S and not P, sorry, not P or S and T. Yep, that makes it well formed too. Are we good so far? Yep, go ahead. That is the purpose, but this is the mechanism. The mechanism is to say what are the atomic well-formed formulae, and then we say if you use an operator, then as long as the number of things you supply to the operator matches what the operator is expecting, and everything that you give the operator is by itself well-formed, then what you are making out of the operator is also well-formed. Because conjunction takes two, right? So if you only give one thing to the conjunction, it is not well formed. If you try to give it three, it's not well formed. If you try to give the negation two things, it is not well formed. But everything you give it also has to be well formed in order for the result to be well formed. So that's where the recursion comes in. Okay, so instead of talking about well formed or not, because those are pretty foreign ways of using those words, let's think about cool cool people, okay, as a group. Okay. So we'll start with elemental cool people. Iraj is cool, okay, and Hermile is cool, okay. Are we good so far? So now we say if as long as you have a group where inside the group you only have cool people, that group is cool also, okay. So that means individually, Iraj is a cool group of people. It's just one person, but we can look at it as a group. Hermile is also cool. Okay, so by himself, he's also a cool group. Let's see, who else should I pick on? Kakashan is also a cool person. Okay, so by herself, she's also a cool group of people. So now you go like, okay, what if Kakashan and Iraj decides to be a group? Okay, is that group also cool? Huh? Right. Yeah. So now you're looking into when you group groups together, you have to play by the number of groups inside the group, right? So the parent group will basically have to specify, okay, this group needs to have two subgroups. So if you try to give it one subgroup, doesn't work. If you try to give it three subgroups, it doesn't work either. But the additional requirement is every group that is inside every subgroup inside the bigger group also needs to be cool in order for the overall group to be cool. So the moment you put tag into one of these groups, it's not cool anymore. But that's exactly it proves my point. You put tag into any group, it's not cool anymore. So thank you, Ari. You just help prove my point. They should rename this class to be meta. It's just about meta stuff. Whatever we talk about, we'll just get to the meta point. Okay. So are we good with what is well formed? Syntactical correctness. All right. So, but using this, you can make a lot of syntactically correct, but otherwise, quote unquote, useless, kind of expressions. P by itself is well formed. We like that. Okay, P and P is also well formed. We like that. That thing NP itself is also well formed. We like that. Take this whole thing, NP again. It is also well formed. I can keep going, as you can see, right? So now I'm going to ask you one question, which you probably know the answer of already. How many well-formed formulae can I make using just that alpha and just that omega? Infinite, exactly. Okay, there's an infinite number of well-formed formulae. Is that okay? So we can also think of this as the space of well-formed formulae. So the space of well-formed formulae is really just a set that contains every well-formed formula that we can conjure up using this alpha and omega. Are we good so far with that concept? It's just a set. It's an infinitely large set that contains every syntactically correct expressions. Okay? Many of those really do not have any meaning because they're really the same thing as many of the other ones. But we can say that okay, there's an infinite number of these expressions. Is that okay? All right. So now we move on to iota. Okay, this is iota. So iota is the set of well-formed formulae that are known to be true. Okay, so I'm just gonna pause. Okay, and these are all in the notes too, by the way, so you can read the notes and highlight the portion that says exactly what I'm saying. So iota is once again a set of expressions or well-formed formulae that are just known to be true to begin with. Don't ask me why. Okay, so let's just say that P is saying Ryan Hermele is cool. Okay, it's a statement. It can be true, it can be false, right? So I can put that into iota. So now you cannot ask me, why is Ryan cool? I don't know. He's just cool. Okay. And then we can use Q and say, okay, Q means Kakashan is cool. Okay. Kakashan is cool is a statement. It can be true, it can be false, right? So I just decide, okay, I'm going to put Q into iota so that it is just a known fact that Professor Kakashan is also cool. Okay. So now we have not zero, not false is true. True is by definition true. Ryan is cool is true. Kakashan is cool is true. So let's just say that R means tech is cool. Okay. So you don't have to always put individual or single variables into iota. You can say not R is true because R means tech is cool. So not R means tech is not cool. So this means not tech is not cool is a known fact. Don't ask me why. That is just a fact. Is that okay? But you can have some other even more obscure expressions too. So let's just say that S is, who should I pick on? Iraj. Okay, how can we forget about Iraj? So let's just say that S is Iraj is cool. Okay, and give me one more professor that has not been named yet. Okay, yeah, Bill Simpson. Okay, teaching physics, right? So we'll say, T is saying that Bill Simpson is cool. So now we can say, well, at least one of them is cool. Okay, are you guys getting the idea? Okay, these are expressions. Okay, the expression itself is known to be true, which means it may not tell you whether it is Iraj that is cool or Bill Simpson that is cool or both of them are cool. We just know one thing, which is at least one of them is cool. Is that okay? All right. So iota is filled with expressions like these, which are your starting points. Okay. starting points for what, right? If you say this is a starting point, that means we're going somewhere. Okay, we should end at some point, right? So this is where the tablet comes in super handy because if you imagine this is the space of all the well-formed formulae, certain of these ones are labeled as true to begin with. They are seeds. So now we go like, oh, okay, this one is known to be true. 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 This one is also known to be true, and so on. So they are starting points. Okay. And then somewhere within this space is an expression, let's say over here. Okay. I want to see if tach is also known. Okay, from this, okay, so let's see what would be the good one to say. So from this, can I say that tech is cool implies Iraj is cool? I mean, that's just me asking, okay? In other words, we can say, does is tech cool implies Iraj is cool, okay? That's that's what this point is representing. But I'm going to use a question mark on top of that because this is not a marked point. It is not known to be true. This is I this is the point where I can say, can we derive from these known to be true points and reach that? Are we good so far? So now the next question is, so how do we get there? I mean, we need to start from these and determine whether we can get to this. So how do we do that? So that gives us that means we need the last set, which is zeta. So the set of zeta is a set of rules. Okay, so you can look at those rules. They're kind of like your algebra rules. Okay, so we have commutative, we have distributive, blah 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 blah. Okay, so when you apply each one of these rules, you are basically going to this picture and go like, hey, if I look at this and apply a particular rule in zeta, that means this point can also be labeled as true. If I take this one, apply a particular rule in zeta, I can also prove that this is true. If I take this one, apply another rule in zeta, I can now say that this is also true, and so on. So every rule in zeta is a quote unquote transformation, but you can look at it as if I can find this to be true and I can find this to be true, they meet the input criteria of the rule, then I can use the output of the rule to say, oh, okay, that means that well-formed formula, which is already in the space, is also true. Is that okay? So now the question is, using all those rules, okay, and we are expanding what is known to be true, or excuse me, I should not say that. We are using what is known to be true to derive what is also true. So we're labeling more and more and more of these expressions in the well-formed formula space. The question is, can you reach this dot here? Hmm? Nope, no, it's not cryptography. This is how we prove theorems. You start with things that are known to be true. You have a set of rules to tell you, hey, if you know this to be true and this to be true, that is also known to be true. And then you can keep going and going. So that is basically what we have here. Before I let you guys go, I want to emphasize one thing. This is the number of transformations in Zeta for human logic application is 20 something rules. Okay, I don't want to deal with memorizing all those rules, okay, or remembering the names of those rules. But the bigger problem that we have is this space is infinitely large. So you can keep applying the rules and keep missing where you need to go. Okay, in other words, which rule are you going to apply next? How do you know that it's going to get you closer to where you need to go? And worse yet, if this point is not really reachable, which is in this case, okay, when are you going to give up and say, Tech, you just gave us a trick question. This expression can never be implied by any one of these. So that is the biggest question. Because in the older days, I guess when propositional logic first came out, or the reason why it came out, is because people already knew this is true already. We just need to find the path to go from here to here. Okay? Yep. Question? Zeta. So zeta is the set of rules. I haven't talked about the format of what the rules look like, but it's in the reading material. And I know you guys have a lot of days before Monday, so read the reading material in preparation of Monday. But I'm giving you a lot of background material today so that you look at those symbols. You're no longer looking at the symbols like, what is this? We know why they're there. Okay. So now the question is, what does a rule look like? And how does it take an instances of well-formed formula expressions and go like, oh, we can apply that rule now. Yep. No, the rules do not govern well-formed formulae. They govern if you know certain things to be true, what is the pattern that tells you what else also needs to be true. Okay. You don't make up the rules in linear algebra. In linear algebra, the rules are already set, right? And you're only told about properties of a certain matrix or certain relations between two linear vectors and whatnot, and then you have to prove a certain statement about some kind of combination of the vectors or matrices or operations of those things. That's a rule. Associative property is a rule. Yep. It means you can move the parentheses in any way and it still maintains the meaning. Yes. So each axiom, right. So the axioms of normal algebra will map to things in Zeta. But the Zeta that we are talking about only works with um, Boolean expressions. Yep. All right. Very good. I'll see all of you on Monday. Yep. Have a good week. And if you want to stay behind and admire the view, please do so. It is.